Okay. So today I want to classify the possible simple roots, the possible root systems. Or I want to start at this classification. But remember, we already started this by looking at 2x2 matrices. So remember what Cartan matrices were. These were matrices that satisfied 3 conditions. So the diagonal guys are 2. These are all integer matrices. Aij is less or equal than 0, and it's non-zero if and only if Hij is also non-zero. And 3, all minors, principal minors, are positive. In particular, if you choose 2 rows and 2 columns of such a matrix, you end up with a 2x2 submatrix that needs to be of the following form, where A and B are both negative numbers. Let me just then put minus and minus. So now A and B are positive numbers, and the determinant of this thing has to be positive, and this is equal to 4 minus A times B. And it needs to be positive. So we see that we have some options. So the options were, well, options are, A and B are equal to 0, both of them. In this case, the determinant is 4. And in this case, the matrix looks like this. And the Dinkin diagram looks like this. And it's not connected. And this root system is not irreducible. The other option is A is equal to 1, B is equal to 3. I guess I'll just go the other way around. Let's go with decreasing determinant. So this is the highest possible determinant, which is equal to 4. The other option is, as soon as A is non-zero, let's say it's 1, then B has to be non-zero, so the minimum possible value is 1. In this case, the determinant is 3. And we are in this situation, and the Dinkin diagram is this. The other option is A is equal to 1, B is equal to 2. The determinant here now is 2. It's 4 minus 2 times 1. Or you can take the transpose. A is equal to 2 and B is equal to 1. And in these cases, the Cartan matrix looks like this, or the transpose. And the Dinkin diagram looks like this. Or it's just flip it. And then we have the case A is equal to 1, B is equal to 3, or its transpose. A is equal to 3, B is equal to 1. The Cartan matrix looks like this. Then we have 3 arrows. And, well, you cannot continue like this forever. If A is equal to 1 and B is equal to 4, this thing already has determinant 0. And if the smallest of A and B, let's say that it's A by transposing, is at least 2, then the determinant of this thing is at the very most 0. So it's less or equal than 0. So you're not allowed to have both numbers bigger or equal than 2. So these are all possible 2x2 Cartan matrices. These are all possible Dinkin diagrams with 2 nodes. Modulo the fact that you can consider this by looking at the transpose of this matrix, or you can consider this by looking at those transpose of those. And the question is, do they come from a root system? And yes, in this they do. The root system for this guy is A2 plus A2. Oh, sorry. A1 plus A1. SL2 plus SL2 is a Lie algebra that gives rise to that root system. So how does this look? I mean, these are all 2 by 2 matrices. And remember that the set of simple roots was a basis for this vector space. So this vector space is a real 2-dimensional vector space. I should be able to draw it. Okay. So let's draw this 4 set of root systems. So the first one is A1 plus A1. The root system simply looks like, well, this is the root system of A1. So let's say this is alpha 1. This is 0. This is minus alpha 1. And now I'm taking the direct sum with another root system, which is just like A. So let's call this guy alpha 2 minus alpha 2. With the standard Euclidean form on R2, so that this guy has, so that this guy has square norm 2. So if you cook up the Cartan matrix for that root system, you're going to find this. Let's look at this one. This one looks like this. This is the root system of A2. And that one looks like, probably I'm not going to fit them all, so probably it's better to put this here. So the root system for A2, this one looks like this. This is my delta. And remember this guy, the roots were of the form EI minus EJ plus or minus those, where 1 is less or equal than I. I think this is the notation that Jethro used with you guys. Less or equal than 3. You can change this number to R plus 1, where R is this rank. So in this case, this root here that I'm drawing there, I'm going to call it alpha 1, and it corresponds to epsilon 1 minus epsilon 2. This root here, I'm going to call it alpha 2. It corresponds to epsilon 2 minus epsilon 3. And how do we determine, on this root system, how do we determine the simple ones? At least this is in rank 2. We should see it immediately. We have a linear functional f that determines a hyperplane in V, which is the zeros of f. And in this particular case, which is rank 2, it's going to be a line in that 2-dimensional space. So choose any line that passes through the origin in this 2-dimensional space. For example, this line. That's f is equal to 0. Everything that is on this line is f is positive. So everything that is here is positive. And we see what are the 3 possible positive roots. This, and that. So these are the 3 positive roots are alpha 1, alpha 2, and this one, which is just alpha 1 plus alpha 2. Now, which ones are the simple ones? Well, in this case, again, it's clear that this one and these ones are simple because f of this has to be the sum of these 2, which is bigger. So the simple roots are alpha 1 and alpha 2 that I depicted there. The same for this. You can just choose this, any line. For example, this line makes alpha 1 and alpha 2, the simple ones and the positive ones. For this guy, the situation is slightly different. We have something like this. I guess. Let me draw this one and not waste more time, because this one is the hardest one, I guess. So this one looks like 2 copies of A2, but of different length. Did you guys do the G2 root system with Jethro? Did Jethro do it? He did? Ah, perfect. OK, so you know that what the G2 root system is. And it looks like this. It looks like 2 interleaved copies of A2. So these are 2 copies of this rotated by 30 degrees, but the length are of 2 types. So these roots here have square root. Let me call this guy alpha 1. This root here has alpha 1 is equal to 2. And the other roots have square norm 6. So again, choose any line through the origin. And you're going to realize immediately that, well, I'm going to choose one particular one. Something like passes between these 2 roots. What it's clear is that between any 2 roots, if you go like in a counterclockwise, for example, you have them alternating small roots with larger roots. So any line that cannot pass through the roots, because the requirement was that this f was never 0 in a root, it's going to have to pass, it's going to have to break the angle between a small root and a bigger root. So any line is going to be something like this. It passes through a small root and a bigger root and a small root and a bigger root. So then it's clear again, once you choose any line, what are going to be the simple roots. In this case, it's this alpha 1 and that alpha 2. And what are all the other positive roots? So here, alpha 2 is a larger root. This is equal to 6. And you see what are the other larger roots. So to alpha 2, you can add 1 copy of alpha 1. So this, what are the simple roots are alpha 1 and alpha 2, which are positive. Then you have alpha 2 plus alpha 1, which is this. Then you have alpha 2 plus 2 alpha 1, which is this. Then alpha 2 plus 3 alpha 1. And that's the whole string from alpha 2 adding multiples of alpha 1. And then the last positive one is this one, which is 2 alpha 2 plus 3 alpha 1. Okay? And these are the simple ones. And this whole thing is delta positive. Well, you see that you have there 6 positive roots total. So there are 12 total roots in this system plus 2 of the rank. That's the dimension of G2. Okay, so today I want to classify, or at least start classifying what are all the possible ones. And I'll divert a little bit from Jethro's argument. So let's start analyzing again systematically all the root systems that we know. Let's look at what are the corresponding Cartan matrices and what are the corresponding Dynkin diagrams and what are the extended ones. Okay, so this is a root system that we have, AR, and we depicted there. This delta corresponds to, so first of all, the lattice, the root lattice, which I guess is Q of AR. These guys were of the form, the sum of AI epsilon I is equal to 1 to R plus 1. I think this is the notation that Jethro used. I'm not really sure. But the sum of AIs is even. And AI is integer. Inside of here, the roots are those alphas that have norm 2. And this corresponds to epsilon I minus epsilon j plus or minus this. 1 less or equal than I less than j less or equal than R plus 1. Just repeating what we did there. Those are the roots. So that's it. So this is my root system. This is inside of a vector space. The vector space V is of dimension R. And this consists of the sum of, probably AI is a bad idea. Let me call it BI epsilon I is equal to 1 up to R plus 1, where the sum of the BI's, it's not even here. This is 0. sum of the pi is 0, r plus 1, and pi is real. So I have an r plus 1 dimensional vector space with basis epsilon I from 1 up to r plus 1, modulo 1 equation, that's an r dimensional vector space. It's a linear equation, that's an r dimensional vector space. So this is my v. This is q inside of v, and this is delta inside of q. So we need to choose a linear function that is non-zero on any root. And the simplest one is, well, to define a linear function on v, I can just tell you what it is on the basis epsilon I. So choose such that f of epsilon I is equal to r plus 1 minus I. And it's a trivial exercise that this thing is non-zero on these roots. Well, simply because I and j are different here. So this thing here is non-zero. It's a well-defined linear functional. So this belongs to v star, and f of alpha is non-zero for every alpha in that. Okay, so now it's clear what are the positive roots out of this. Delta plus consists of roots of this form where f is positive. Well, but if I is less than j, then f of epsilon I is bigger than f of epsilon j. So f of this thing is positive, and f of minus this thing is negative. So therefore, delta plus consists of those roots with a plus sign. Epsilon I minus epsilon j, where 1 is less or equal than I, less than j, less or equal than r plus 1. Now the simple ones. Well, we notice that f takes integer values. And it's never 0 on roots. So the minimum possible value that f can take is 1. And we know that f takes value 1 on the following roots. Epsilon 1 minus epsilon 2, epsilon 2 minus epsilon 3, and so forth, up to the last one, which is epsilon r minus epsilon r plus 1. F on this guy is 1, which is the minimum possible value for such an f which takes integer values. And these guys are clearly linearly independent. They are r of them. So therefore, they span the whole vector space V. So this has to be the simple root system. So that is the simple root system. Let's look at the Cartan matrix and the Dinkin diagram. So I'm still on AR. Well, all roots have norm 2. But then if I call the simple ones from alpha 1 up to alpha r, so alpha I is epsilon I minus epsilon j, then it's clear that each one of them has norm 2. So alpha I is equal to 2. Also, it's clear that alpha I with alpha I plus 1, oops, I want to stop me. This is alpha I. It's clear that alpha I with alpha I plus 1, the inner product of these two, well, is the inner product of this with epsilon I plus 1 minus epsilon I plus 2. So the inner product of those two things is equal to minus 1. And it's also clear that, well, therefore, epsilon, so alpha I with alpha I minus 1. So here, this makes sense whenever I is bigger or equal than 1 and is less or equal than r. Less than r. And this one makes sense whenever I is bigger or equal than 2 and is less or equal than r. That's correct. This is also minus 1. And otherwise, 0. Alpha I with alpha j is equal to 0 if the distance between I and j is bigger or equal than 2. Okay? Because they don't share any of these epsilons in common. The inner product is clearly 0. So the Cartan matrix for this thing looks like this. It's an R by R matrix with 2 on the diagonal. 2's on the diagonals. And alpha 1 with alpha 2 has an inner product which is -1. Alpha 2 with alpha 1 is an inner product which is -1. And then I have -1 on this off diagonal. And it's clear that these numbers are this because remember the entry. I think I'm going to be at least consistent in my choosing either the right matrix or the transpose. But I think I've defined this to be twice alpha I, alpha j, over alpha I, alpha I. So since all of the roots are of square norm 2, this 2 cancels this 2, and it's just the gram matrix of that inner product, which is computed. Okay? So that's the Cartan matrix. So what is the Dynkin diagram? I have the one that corresponds to alpha 1. I have the last simple root which corresponds to alpha r. And any two consecutive roots are connected by only one arrow. So it looks like this. Okay, so what's the highest root? Well, we know this is a connected, this is an indecomposable simple root system. This is a connected Dynkin diagram. And probably I did not prove that. But it's an easy exercise, and I think it probably is an exercise that Jethro left in the homework. Prove that a root system is indecomposable if and only if its Dynkin diagram is connected. And it's a trivial proof. If you have a disconnected Dynkin diagram, then take the roots for each one of the connected components, and they're going to be on they're going to span orthogonal subspaces. All right, so this is connected. So we know that there exists, in last class we proved that there exists a unique maximal root. What is that maximal root? Well, we have a candidate because we have this linear functional. So we can try to look for what is the maximal value that functional takes. And indeed we can find it because since these guys are ordered, we know that epsilon 1 takes the highest possible value for f. So we would want to have epsilon 1 with a positive number. And we would want to subtract the one that takes the minimum value for f. So we have a candidate, and it's trivial to check that has to be the guy, which is theta is equal to epsilon 1 minus epsilon r plus 1. F takes maximum value there because it takes maximum value on epsilon 1, and it takes minimum value on epsilon r plus 1. So that means that alpha 0, remember, was minus this thing, is epsilon r plus 1 minus epsilon 1. And I need to enlarge this Cartan matrix by adding alpha 0. So this is the extended Cartan matrix. I'm going to add one row and one column that corresponds to alpha 0. So alpha 0 has inner product with what? So alpha 0 has only non-trivial inner product with alpha 1, which is epsilon 1 minus epsilon 2, and with alpha r, that is epsilon r minus epsilon r plus 1. So alpha 0, alpha 1 is equal to minus 1, and alpha 0, alpha r is equal to minus 1, and all the other ones are 0. Alpha 0, alpha j is equal to 0 otherwise. So if j is not 1 or r. Oh, that's a bad idea. Or 0 as well. Alpha 0 is clearly 2. So this extended Cartan matrix has still a 2 in the diagonal. It has a minus 1 here, minus 1 here. But it also has a minus 1 on the last entry and a minus 1 on this last entry. And everywhere else is 0. So what is the Dynkin diagram? The extended Dynkin diagram for this thing is, well, I'm going to add alpha 0 here. Probably a different color is better. I'm going to add alpha 0 here. And it's connected with one arrow here and one arrow there. Okay? So that's the extended Dinkin diagram. Now, a trivial exercise is to check that the determinant of this Cartan matrix for AR, for A, so the Cartan matrix, I guess I should use instead of A, I should use C. But anyways, for that Cartan matrix extended is equal to 0. So it's certainly not positive because, well, I'm just adding one vector that is certainly not linearly independent with the previous ones. Okay? These were a basis for that vector space. And I'm just taking a gram matrix for a set of vectors that are not linearly independent anymore. So it is still the gram matrix of an inner product. It's just that now I'm taking more vectors than just a basis. So the determinant of this thing is non-positive. So that can never be the roots. This can never be the Dinkin diagram of a semi-simple Lie algebra, because we've proven that the Dinkin diagram comes from an actual Cartan matrix, and this cannot be a Cartan matrix. So the inner part it is, the extended one is not. So as a corollary of this, since, by definition, since you have a Cartan matrix, so an obvious observation, let A be a Cartan matrix. And choose and A prime a principal minor. So a principal submatrix. By this I mean choose R rows and the corresponding R columns, and that determines an R by R submatrix of A. Then this guy is also a Cartan matrix. So that means that if the way we're going to use this typically is the opposite. It's the converse of this. That if A prime is a principal submatrix and it's not a Cartan matrix, then we couldn't have started with a Cartan matrix. In particular, if I give you any Dinkin diagram that has as a subgraph by just choosing the nodes and all of the corresponding arrows connecting those nodes, this thing, it cannot have come from a simple Lie algebra. So no Dinkin diagram can have a simply connected loop. So as a corollary of this, no Dinkin diagram has a loop consisting on simply connected. And by simply connected, I really mean just between two nodes, there's one arrow. Nodes. We haven't ruled out a loop of the form like this. This may happen for all we know. But we do know that there's no loop where all the arrows are just simply laced. So by the way, I think I didn't give that definition. A simply laced Lie algebra, or a simply laced Cartan matrix, or a simply laced Dinkin diagram is such that the corresponding Dinkin diagram is a graph where all arrows, if any, is just one simple arrow. So between two nodes, either there's no arrow or there's one arrow, but not two or three. The lacing number of a Dinkin diagram is the largest number of arrows between two given nodes. So for G2, that's 3. For B's and C systems is 2. For all simply laced is 1. OK, so we finished with AR. And probably I want to keep one word with this datum. So let's keep AR, a summary of AR here. So we have AR, and it is a diagram like this. Alpha 1 up to alpha r, and some alpha 0. And this is the extension. OK, so let's go for BR. Let's do this here. And let's go slightly faster. So someone can tell me, what are the root systems that Jethro described? Did he do all of them? Like, did you guys do the A, B, C, D series and the E? Exceptional ones, F4 and G2? With more or less, OK, so he didn't give all details on all of them. OK, so I'll just, if there's something that is not immediately obvious, stop me. I hope AR was completely clear. BR is going to consist of the following. I want to rush a little bit because otherwise we're not going to finish at all. But so the root system for these guys, so delta is going to consist of roots are of the following form, epsilon I minus epsilon j. So the same things that we have for AR, it's just that now we're going to have arbitrary signs for these things, where I, so 1 less or equal than I, less than j, less or equal than r. So it's no longer r plus 1 here. But we also have plus or minus epsilon I, where 1 less or equal than I, less or equal than r. OK. So the lattice, you see immediately what it is, because the lattice is just ZR. Right? Since I have a basis of z to the r, and these guys here are linear combinations of those. So then Q is just z to the r. The basis is just epsilon I. So as an example of this is the rank 2 basis that I didn't give you. But now we can draw it. We have epsilon 1, epsilon 2, minus epsilon 1, minus epsilon 2. And then we have epsilon 1 plus epsilon 2, which is this guy, epsilon 2 minus epsilon 1, and then the negative of those two. Okay? Yeah, some horrible drawing. This should be like this. This should be in the same vertical. So that's B2. That's, OK, so that's the root system. Again, let's choose a linear functional, which I want it to be something like this, a line like this in this case, so that this and this are the simple roots. Let's do this in general. And I'm going to do this. I'm going to take the same functional that I did before. So f of epsilon I is going to be r plus 1 minus I. So that epsilon 1 has the largest value for f, and epsilon r takes the smallest value for f. OK? OK, so what are the simple roots? Again, this takes values on the integer numbers. So we're looking for the minimum possible thing is f is equal to 1. And then immediately we have some roots that take that minimum value, which are of the form epsilon 1 minus epsilon 2 up to epsilon, the same for AR, epsilon r minus 1 minus epsilon r. So for those, f is 1. But the problem is that now they don't span the whole vector space because there are r minus 1 of these guys. But what it is clear is that then again, epsilon r, which is the largest one, also takes values 1. So we can just add epsilon r here to this list. And f of this is 1. So all of these are clearly linearly independent. They span a vector space of dimension r, which is the real vector space generated by this Q. So if you take R tensor over Z over with Q is that. So therefore, this has to be the simple root system. What are the positive roots? Well, out of this, the ones that are of the form epsilon I minus epsilon j, where I is less than j. And out of those that are plus epsilon I and not minus epsilon I. So this is my simple root system. So let's call this guy alpha 1. Probably it's not the same order that Jethro used. This is alpha r minus 1, and this is alpha r. Let's add alpha zeros right now so that we start with the extended diagram. So what is alpha 0? Now I'm looking for the largest possible value for f. So epsilon 1 again needs to be positive, and then I want to add something more. So I'm going to add the two largest values for f, and that's clearly is going to be theta. So alpha 0 is going to be minus that, and it's going to be minus epsilon 1 plus epsilon 2. Okay? So epsilon 1 plus and epsilon 2, they take, f takes the largest possible value on these things. So therefore, this is theta, and therefore minus theta is this alpha 0. Okay, so what's the Cartan matrix for this? And let's do the extended one directly. So alpha 0 has square length 2, and all of these roots have square length 2, except the last one, alpha r, that has square length 1. So we have 2 on the diagonals everywhere, except the last one that has a 1. How about this? Well, this looks like an AR minus 1. So each one of them is connected to the next one. So I have a minus 1 here, a minus 1 here.
How can we not have the 2 on the diagonal?
Oh, I'm sorry. That's correct. This is a 2 on the diagonal. Just the square root is 1. Thank you. Yeah, so AII is always 2, but in particular is 2 alpha I divided by alpha I, which is the reason we have that 2. But yeah, we're going to need the fact that alpha r has square length 1. I'm going a little bit too fast. All right, so we have these minus 1s up here. And then there's something funky that can happen on the very last one. So let's check what that is. So the last root, so this r minus 1, against what doesn't have a 0 positive product, inner product? Well, it doesn't have a 0 inner product with the previous one. That's the minus 1 that we see here. Okay? So this is the minus 1 that we see there. However, this entry, the entry r plus 1, r minus 1, and r, I see a non-trivial inner product. I see a minus 1. Okay? So alpha r minus 1, alpha r is equal to minus 1. Therefore, with my convention, which I still don't claim it's the right convention, but what we see is that a r minus 1 r, this is equal to 2 times this number, which is minus 1, divided by alpha r minus 1, which is the square length of this guy, which is 2. So alpha r minus 1 r is minus 1. But alpha r minus 1 is 2, that same inner product, divided by the square length of this guy, which is 1 now. So I see a minus 2. Okay? So this is how this guy looks. Now let's look at alpha 0. So alpha 0, which is this thing, has a non-trivial inner product. Well, I see an epsilon 1 here, but unfortunately I also see a minus epsilon 2 here. So against alpha 0 is perpendicular to alpha 1. Okay. But alpha 2 has an epsilon 2 minus epsilon 3. And this guy, inner product with this, well, I have a minus epsilon 2 here and a plus epsilon 2 here, so that's a minus 1. And both of them have square length 1. So this guy is perpendicular, but this one is not. So there's a minus 1 here in the second entry, and the same here about this. Everything else is 0. So that's the Cartan matrix, and that's the extended Cartan matrix. And by the same reasoning, this extended Cartan matrix is not a Cartan matrix. It's the same as AR. So the inner part is the Cartan matrix of BR, and you know that SO2R plus 1 generates this Cartan matrix. Hopefully Jethro did that. But this larger one cannot be the Cartan matrix of a Lie algebra. So again, this Lincoln diagram, how does it look? Well, we have alpha 1 up to alpha r minus 1. This looks really like just an AR minus 1. This is this Cartan matrix up to here is the Cartan matrix of AR minus 1. Then we're adding an extra node for alpha r. And alpha r is connected to alpha r minus 1. But now there are two rows, because I have this minus 2 here. And since alpha r is smaller than alpha r minus 1, this rows is directed like this. So that's the thinking diagram of BR, and the extension is adding an alpha 0 that is connected to, within one arrow, to alpha 2. This is the extended diagram. Okay, let's do CR. Oh, I'm horrible. I'm going to need 2 boards just to draw the thinking diagrams. Okay, so let's do CR. All right, so CO again. So delta looks very similar to that. So this is this looks like plus or minus epsilon. Yeah, I think that I got correctly. Okay, so plus or minus epsilon I minus epsilon j. I don't think I'm going to have time to do the interesting ones. So this is going to be interesting. So I don't know if I should move to I don't know if I should be doing the D case and the E cases. Okay, so let's see how fast we go. Otherwise, I'm going to just take one extra class in Jethro's. All right, so I'm going to take this, guys, and I'm going to have plus or minus twice epsilon I. So again, same rule. 1 less or equal than I less than j less or equal than r. And here 1 less or equal than I less or equal than r. Same linear functional. So let's do this quickly. So I'm going to take the same linear functional, but now the set of simple roots is slightly different. So I'm looking for the minimum value for f. And what I notice is, again, that epsilon 1 minus epsilon 2 takes 1 as f value. Epsilon r minus 1 minus epsilon r takes 1 as value. But then I'm in trouble that the minimum possible value. So these are all the ones that f takes 1 as value. Okay? So any other f evaluated in any other root is going to have at least 2. So it's not enough, the argument that I gave before. So now we need to look into a different argument for to find what is the missing simple root. Then again, epsilon r is the minimum possible value for f. Remember that f on epsilon r is 1. And then therefore f on twice epsilon r is 2, which is the minimum one. But there are other roots where you can have a 2. You can take epsilon 1 minus epsilon 3, and f of that is also 2. So if you look at what are the possible ones such that f takes 2 as value, well, there's this one, and then all of the other ones are of this form. So if I include one of that form, those are linear combination already of this, because we already knew what is the basis for AR. So that would never be a basis of the vector space. So this can be the only root with f taking value 2, which is the minimum possible after 1. And these are all the ones that have 1. So this guy has to be included, otherwise we don't cover the whole vector space. And this is our simple root system. We get again what are the positive roots are of the form epsilon I minus epsilon j, where I is less than j, and all the positive ones here. So this is alpha 1 up to alpha r. This is alpha r minus 1. What is the largest root? Well, in principle, before we took epsilon 1 plus epsilon 2. But now, epsilon 1 plus epsilon 1 has a larger f. So that's the largest root. So alpha 0 is equal to minus 2 epsilon 1. All right, so now the square length of the roots are 2 for all of these guys and 4 for this guy. In particular, how does C2 look? Okay, so this is the case, well, r is equal to 2. So I have plus or minus twice. So this is 2 epsilon 1. So here's epsilon 1. This is 2 epsilon 2. And they're negatives. And here I have epsilon 1 plus epsilon 2, epsilon 1 minus epsilon 2, and so forth. So you see that this diagram, C2, is the same diagram as B2, just rotated and scaled. So C2 really looks like V2, it's just that it's rotated and scaled. For B2, the square lengths were 2 and 1, and for these guys are 2 and 4. All right, so that's C2. This is the simple root system. And what is the Dinkin diagram? What is the Cartan matrix? Let's do the extended one as well. So we have 2 on the diagonals. Thank you for noticing that. So we have an AR system from alpha 1 up to alpha r minus 1. So let's put this last 2 here. We have minus 1s like this. But now the inner product of alpha 1 with alpha r minus 1 with alpha r is minus 2. So A r minus 1 r is equal to 2 times. The inner product between these two guys is minus 2 instead of minus 1. And then I need to divide by the square length of AR minus 1, which is 2. So I get a minus 2 now here instead of a minus 1. And if I do this on the transpose, this is 2 times, again, minus 2. But now I need to divide by the square length of that, which is 4. So here I have a minus 1. The same thing for alpha 0. Well, alpha 0 is slightly interesting now because now this guy has only non-trivial inner product with the guys that have an epsilon 1, which is this alpha 1, and nothing else. So the inner product of alpha 0 with alpha 1 is minus 2. Okay. So I need to do A0, 1 is equal to 2 times this inner product, which is minus 2, divided by the square length of alpha 0, which is 4. So I get a minus 1 here. And if you do this for A10, you're going to need to divide by the square length of this, which is 2. So you're going to get a minus 2 here. Okay? So the Dinkin diagram for CR is very much the same as for BR. The only difference between the Dinkin diagram of CR and BR is that this double arrow here goes in the other direction because this guy has square length 2 and this guy has square length 4. And alpha 0, the extension, is actually substantially different. Before we added this extra node, now we're adding this other node, alpha 0, that connects non-trivially with this alpha 1. It has 2 arrows, and alpha 0 is larger than alpha 1, so it goes like this. So that's the extension for CR. Same argument. So whenever you see a sub-Dinkin diagram that is like the extended one, it cannot come from a Lie algebra, from a finite dimensional simple Lie algebra. In fact, well, those are the Dinkin diagrams associated to certain interesting infinite dimensional Lie algebras. If Kac-Moody affine Lie algebras have those as Dinkin diagrams. All right, so let's do D. It's much slower than I had hoped for. All right, so for DR, the root systems are just simply these guys, epsilon I plus minus epsilon j. Again, root system is this, where 1 less or equal than I, less than j, less or equal than r. So all of the roots have the same square length, which is 2. So we know that this is going to be simply laced. So what are the possible, the simple roots? Well, the same argument, same linear functional f would give us epsilon 1 minus epsilon 2 up to epsilon r minus 1 minus epsilon r. And now we're in trouble because now these are all the roots such that f takes values 1. So these are simple. But I need to choose another one. And it cannot be of the form epsilon I minus epsilon j because it's already a linear combination of this. So it has to be of the form epsilon I plus epsilon j. And I want it to be minimum value for f. So there's only one thing that can be, which is epsilon r minus 1 plus epsilon r. So these are the two guys that take minimum value for f, and they have to be positive. So there has to be this. So this is alpha 1 up to alpha r minus 1. This is alpha r. This is the simple root system. That's clearly a basis of the whole vector space. So what's f alpha 0? Well, same argument. I need it to be maximum for f, and we know it exists. Well, we're going to see that this Dinkin diagram is connected. So we know there exists a unique one. So, and the maximum value for f here is clearly the following. So alpha 0 is, well, epsilon 1 and epsilon 2 take maximum value. So it's going to have to be minus that. All right, so Cartan matrix for this thing. Now this is simply laced, so there's only going to be minus 1s everywhere, simply because all of the involved roots have the same length. Okay, so we still have an AR here, an AR minus 1 there. Then something funny happens here in that these two things are orthogonal. So these guys are not connected. I have zeros here. But what I see is that alpha r minus 2, which is epsilon r minus 2 minus epsilon r minus 1, does have a non-trivial inner product with this. So here I have a minus 1, and here I have a minus 1. The same thing for this alpha 0. So this alpha 0 has non-trivial inner product. Well, this thing is perpendicular to alpha 1. But alpha 2 is epsilon 2 minus epsilon 3, and it has a non-trivial inner product with this. So here I have a 0, and here I have a minus 1. And then everything else is 0. So this is the Dinkin diagram for dr. Let's do it here. So dr looks like this. You have alpha 1, and up to alpha r minus 1, it's always an AR type. Then alpha r is not connected with this. Alpha r is connected with this. So that's dr, and the extended diagram is alpha 0, which is connected to alpha 2. Okay, so that's D. Let's go with the E systems. I hope Jethro talked about even lattices. Did he? Good. All right, so you know all the even lattices. So what I presume is that Jethro didn't tell you what are the simple roots because he couldn't have for the E system. So let's take some time in writing those. Okay, and let's figure out the Dinkin diagram for these systems. So the E8 system is the basis for all of them because this comes from an even lattice, and this is a general theorem that if you have an even lattice, you look at the roots inside of that lattice that have of square length 2, and that's a root system. So that's how you construct E8. And the lattice itself is interesting because it consists of guys that are of the form AI epsilon I, where the AIs are either integers, all of them, or all of the AIs are half integers. And you require that the sum of this thing is even. So again, I is equal to 1 up to 8. So the root system consists of epsilon I plus or minus epsilon j. Again, 1 less or equal than I less than j less or equal than 8 now. So those are the easy ones. But then you also have 1/2 of plus or minus epsilon 1 plus or minus epsilon 2 plus or minus epsilon 8. And there's a bunch of those. So there's, 2 to the 8 of those. You get to choose the signs of each one of those. So this is the root system. And now I need to be careful on how do I find the simple ones and what are the positive ones and so forth. So you cannot play the same game as before because if you just choose.
I think we also need some conditions.
Oh, yes, the number. Thank you. Thank you, because I wanted this to be the sum to be even. So even number, thank you, even number of plus or minus signs. That's correct, thank you. So the reason we cannot use the same argument as before of taking f of epsilon I to be 9 minus I is that that thing is going to end up being 0 in some of these roots. So to make sure that it's not, we're going to do the same thing. We're going to take a linear functional that f of epsilon I is equal to 9 minus, probably I want it to be 8 minus I. It doesn't matter if in epsilon I is 0. So this is for I is equal to 2 up to 8. So epsilon 8, f takes value 0. On epsilon 7, it takes 1, and so forth. But to make sure that, I'm gonna make epsilon 1 very large for the f value. So you can take f of epsilon 1 to be 10 million. It doesn't matter which number it is. It has to be a linear function. I can choose whatever I want. You can take it to be 10 million. I think 32 is the minimum one that this works. So this defines a linear functional. And a trivial exercise is to check that this is non-zero in any of these roots. So if you choose it to be 10 million, then it's easy to check that it's non-zero in any of these roots, and that's enough for all of what I said. Okay, so what are the simple roots? Keep in mind f of epsilon 1 to be 10 million if you're skeptical about 32. Okay, so I'm looking for the minimum value of f. Again, I've chosen this thing to be integer. There's some subtlety here in that I need to check that this thing, that f on this thing is going to be an actual integer. But since I have this condition that there's an even number of minuses, this is going to hold if I choose f of epsilon 1 to be an even number. So I couldn't have taken 10 million minus 1. But f takes integer values, so therefore it takes 1 as the minimum value, and that gives me immediately a bunch of roots. So epsilon 1 minus epsilon 2 up to epsilon 7 minus epsilon 8, these are good roots. These are minimum values for f, so and they are linearly independent. So those 7 roots have to be simple.
Why the first one is simple if we take...
Oh, shit. Yeah. That's correct. It's the opposite way around. I needed 7 roots, and those, yeah. You're absolutely right. So epsilon 2 minus epsilon 3 up to, yeah. And this one was correct, yeah. Up to epsilon 7 minus epsilon 8. Yeah, you're absolutely right. So those are fine. And now, well, we need to play, what are the other simple roots? So this f takes values 1. I don't want to remove this. F takes values 1 on these guys. So pi at least includes these guys. And now I want to know what are the remaining roots. Can anyone guess them? How do we argue?
Epsilon 1 plus epsilon 2 minus all the other ones. So divided by 2.
Okay, so yeah, so let's argue about that. Sorry?
Because we need at least one root.
Good. That's a very good argument. So we cannot span the whole vector space with these guys because these are not linear combination of this. So we need one of this. So let's pick the minimum value for f for that. And unfortunately, epsilon 1 was chosen to be so large, or fortunately, that if I put this epsilon 1 with a minus sign, everything's going to be negative. And f has to be positive. So epsilon 1 has to come with a plus sign. Okay? So that's almost what you wanted. So I'm going to take plus epsilon 1. Let's add this here. Epsilon 1 with a plus. Now I need to have at least one extra plus sign. Okay? And I disagree with you on what the...
I was wrong. We need to take epsilon 8 with plus sign.
Correct. So we want the minimum value for f. And at least we need to add something. So we're going to add epsilon 8. Because this guy has the minimum value for f, which is 0. And then we're going to subtract all of the other ones. Good. So this is one root. So if I call this guy alpha 2, just because it starts with a 2, and I call this guy alpha 7, probably I'm going to get the wrong ordering for the roots. It doesn't matter. This is just a matter of labeling. And I'm going to call this guy alpha 1. Okay? So, all right, so it's clear that these are linearly independent. But now there are 7, and the root system has dimension 8. So I need one more. And here the choice of f is actually going to play a role. So I could have taken 10 million, and it's going to give you something. Or I could have taken this, or probably something smaller perhaps, and it's going to give you something different. So let's think about this. So what is the one that we're missing?
other than 2, I think. So we also
With
need root with
no, so
different number of plus signs.
okay, so the argument here is the following. The argument is that this, so I'm going to start taking linear combination of these guys. And, okay, so if I add any two of these guys, I will have always a plus and a minus, or two pluses and two minuses. Right? So if I add this with something that is not connected, I'm going to have two pluses and two minuses. So now the question is, what happens if I add something like that in that root lattice with something like this? And it's not clear to me that statement that you're making. So the statement is, this thing is going to add some plus signs, and it's going to subtract the same number of minus, or it's going to add the same number of minus signs, and therefore you are still going to be kept with the same number of signs here. But that's not entirely clear to me. Although it's good. So let's just try by experiment. One argument would be, still think of f dictating everything. And let's try to still think that f has to be the minimum possible. Okay? So if f of epsilon 1 is 10 million, all right, then it doesn't matter if I take it to be on these guys. So this is always going to be of the order of 10 millions divided by 2. And among these roots, if I use epsilon 1, this is going to be of the order of 10 millions without dividing by 2, which is a very large number. And if I only use this, I'm never going to get to, if I only use these roots, I'm never going to construct one of those with the same sign. Never going to construct epsilon 2 plus epsilon 3. And by adding multiples of this, I'm always going to include epsilon 1. Epsilon 1 does not appear in this set of roots. So therefore, I'm guessing that epsilon 7 plus epsilon 8, which is really a minimum value for f. And actually, I should have guessed that before, because on epsilon 7, this thing is 1. And on epsilon 8, this thing is 0. So epsilon 7 plus epsilon 8 is certainly not in the linear span of these guys. F is minimum, so we know already that this guy is simple. But also, that argument makes it so that it's the only thing that I can add, because if I take linear combination with these guys, I'm going to include an epsilon 1, and f is much larger. So this is going to be my alpha, and I think I've chosen the wrong order in any ways. I'm going to relabel them in a bit. But these 8 guys are certainly the minimum ones, and these are the simple roots. Okay? But I just wanted to be clear that we could have just immediately guessed this by knowing that f is 0, f 1, but also we're forced to add these things, because any linear combination of these things is going to have an epsilon 1, and I can never get to write this as a linear combination of only these roots. So this one wasn't even in the linear span of these roots. All right, so these are my 8 roots. So now what is the maximum root? We know that I'm going to show that this Lincoln diagram is connected. So what is the maximum root? Well, now f actually plays a role. And if I take f to be 10 million, then it doesn't matter how I choose these guys. F is going to be of the order 10 millions over 2. Whether in these ones, I'm going to have something of the order 10 million. So the maximum possible value for f, let's write it here. Alpha 0 is going to be minus theta, and theta has to have a plus epsilon 1. And then the other one, it doesn't really matter which of the order, but it has to be epsilon 2, which is the largest one. The f takes the largest value. So this is my alpha 0. All right, so I'm not going to write the Cartan matrix. Let's do the Dinkin diagram. Well, let's do them all here. and probably we're going to need to change the names for these things. So alpha 2, the way I've defined them, has a non-trivial inner product of 1. By the way, notice that all of the roots, this was simply laced by definition. The roots have square norm 2. So there's not going to be a double arrow. So alpha 3, alpha 4, alpha 5, alpha 6, and alpha 7 are connected like this. So this is an A6. So those are the 6 roots there. Then we added that alpha 1. And I wonder against what that thing has a non-trivial inner product. Well, let's do the alpha 8, which seems simpler. So alpha 8 is perpendicular to alpha 7, right? But it has a non-trivial inner product with alpha 6, which is epsilon 6 minus epsilon 7. So here I'm going to have alpha 8. And where do I have alpha 1? Does alpha 8 have a non-trivial inner product with anything else? Well, notice that alpha 8, so the only thing that has, so these are perpendicular. Alpha 6 has a minus epsilon 7, and then all of the other ones don't have even epsilon 7 or epsilon 8. So it's perpendicular to all of these other roots. How about this one? Well, epsilon 7 and epsilon 8 appear with different signs here. So this is perpendicular. Alpha 8 and alpha 1 are perpendicular. So I've covered all of them. So now I'm missing only alpha 1 connected with what? Well, I need to take inner product of this alpha 1 with things here. And I see that I have an epsilon 2 on alpha 2. But then epsilon 2 and epsilon 3 appear with different signs. And here they appear with the same sign. So alpha 1 is perpendicular to alpha 2. Then I look at alpha 3, which is epsilon 3 minus epsilon 4. They appear with different sign. And here they appear with the same sign. So they are perpendicular. So where is the one that appears with the same sign? Well, I see that epsilon 7 minus epsilon 8 here appears with different sign, and here it appears with different signs. So alpha 1 and alpha 7 are connected. And that's the only one that is connected. So I should have changed the names of the last 2 roots to be alpha 8 and alpha 1. But it doesn't matter. It's not going. It's just a matter of names. Okay? So this is the thinking diagram of E8. Now, how about alpha 0? So alpha 0 has epsilon 1 and epsilon 2 with different, with the same sign. And it connects with alpha 2. And it has an inner product with alpha 2, which is non-trivial. This is the extended thinking diagram for E8. So that's E8, and that's the extension. Okay, E7, let's do E7 and E6 quickly. Then I'll do F4 and G2 in the next class, because I do want to classify all simply laced ones. We're going to run quickly over the classification of simply laced cases. Okay, so E7. The root system for E7 consists of all of those roots in E8 that are perpendicular to the root that takes all of the sums here being positive. So there's one root here, which is epsilon 1 plus epsilon 2 plus epsilon 8. All of this is divided by 2. And E7 consists of those roots that are perpendicular to that. So it's not hard to realize that that consists of, well, you lose half of these roots immediately, because this guy, the guys that have the same sign are not going to be perpendicular to those. So you're going to have only epsilon I minus epsilon j plus or minus those. And of the other ones, well, in order to be perpendicular, the only thing that matters here is the number of plus signs. So you need to have 4 pluses or 4 minuses. Okay. because the only thing that you count is the number of signs. And that's the root system for E7. Now it's trivial to check that this is a root system. I think probably Jethro already did it, that you have this vector space with the root system. With this lattice, you take a perpendicular hyperplane, the intersection of the lattice of E8 with this perpendicular hyperplane is a lattice. That's trivial. And then you check that it's an even lattice. Therefore, the roots that have square norm 2, which are the roots of E8 that intersect with that lattice, have to be a root system. So therefore, this is a root system. So what are the simple roots? Well, again, you can just take f to be this thing and f of epsilon 1 to be 10 million. So same argument, you have alpha 1, well, alpha 2 is epsilon 2 minus epsilon 3, up to the last one is alpha 7, which is epsilon 7 minus epsilon 8. So f of those guys is 1. And I have, well, I need to add one more. So these are six roots, and I need 7 of them. So what can I add? Well, I don't have anything like this. So I don't need to worry about this. And I need to include at least one of these guys with a half sign. So same argument that you gave me before. So now I need to include the thing that has the minimum possible value for f. So it has to be alpha 1 being equal to epsilon 1. Well, it's going to be 1/2. 1/2 of epsilon 1 needs to be positive because f of that thing is 10 million. And then all of the next ones are going to be negative because I just want to minimize f. But I need to include 4 pluses, and I need to include 4 minuses. So epsilon 2, epsilon 3 is negative, epsilon 4 is negative, and epsilon 5 is negative, and the next ones have to be positive. Okay, so what's the largest one? Well, anything that includes f, epsilon 1 has f of the order of 10 million. So the largest one has to be epsilon 1 minus something. And I want to subtract something that is minimum for f so that the thing is maximal for f. So it has to be epsilon 1 minus epsilon 8. So alpha 0 is minus that. Okay. So what is the diagram for that? Again, we start with alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, and alpha 7 is my A6. And now I added alpha 1 against what this thing has a non-trivial linear product. Well, against alpha 2, this guy has different signs for epsilon 2 and epsilon 3, and this guy has same signs, so it's not. So the only thing that is going to change is when I get to this point, which is epsilon 5 minus epsilon 6, that here they have different signs, and alpha 5 satisfies the same property. Alpha 5 is epsilon 5 minus epsilon 6. So I see that I have a non-trivial linear product against alpha 5, which is this guy. So it looks exactly like this, just that I removed the first node. So if you remove this node, that's E7. So now what's the extension? Well, alpha 0 is epsilon 1 minus epsilon 8. Against what does it have a non-trivial linear product? Well, 1 and 8, they have different signs there, and here they have the same sign. So it's perpendicular to this funny-looking root. Alpha 0 is perpendicular to alpha 1. Yeah, I didn't label it. So it's perpendicular to this. But you see it immediately here. So it has to have either an epsilon 1 or an epsilon 8. None of this guy has an epsilon 1, and this guy has an epsilon 8. So it's non-trivial linear product with alpha 7, which is this guy. So this is the extended E7 diagram. I'll leave you as an exercise to do E6, because I won't have time to classify them. But E6 consists of, out of all of these things, you take alpha 7 and take the perpendicular to that. So E6 has the following form. You play the same game that I did now. So 1, 2, 3, 4, 5. That's correct. So that's E6. So it's just exactly like E7, and you just remove one node. So now this guy has a symmetry. Has the symmetry that you can exchange these two branches. The E7 diagram did not have a symmetry, and the extended diagram added a symmetry. The E8 guy did not have a symmetry, and the extended guy made it even less symmetric. E6 has a symmetry, and the extended guy is going to add a symmetry as well. Is this. So this is C6, and that's the extension. OK. So I'm going to take a different approach than Jethro, but please read Jethro's lecture notes based on the Weil group of the Lie algebra to classify the simply laced and thinking diagrams. But now that we went through the work of writing them all and computing their extended diagrams, then we can exploit that. Theorem, out of all simply laced Lie algebras or simply laced thinking diagrams, theorem, the possible simply laced diagrams are AR, BR, CR, oops, AR, DR, E6, E7, E8. So this guy for R bigger or equal than 1, this guy for R bigger or equal than 2. Proof. And we don't need much time to prove it. So first observation, there's no loops. No loops. Because if you had a loop, then you would have AR extended. That has a loop. So if you have a subdiagram that is not a Cartan matrix, then you're not a Cartan matrix. Okay. So the second observation. No more than one node with valence more than 2. Because if you had such a thing, then you have DR extended. DR extended has 2 nodes that have this balance, bigger or equal than 2. So this is because of DR extended. Third, no node with valence, or probably I should have switched these 2 as well, with valence bigger or equal than 4. So there's no node that has 4 incoming arrows. And again, this is because of the case D4. In D4, these 2 nodes are the same. So in D4 extended, you have this node that has more than 3 incoming nodes. So after you apply this, you recognize that now we're going to classify them by the number of nodes where you have valence bigger than 2. So if there's no node with valence bigger or equal than 2, the possibly simply laced thinking diagrams, connected thinking diagrams. Connected. So if every node has valence either 1 or 2 and you're connected, that's the only thing that you can have. So this is AR. If there is one node where there is a bifurcation, we know that this bifurcation cannot be of valence bigger or equal than 4, so it has to be 3. So this is the only thing that can happen is that you have one node where this thing bifurcates, and it looks like this. It cannot have another one because we've already ruled that out. And it cannot have a higher valence for this node because we ruled that out for default. So these are the only possible Dynkin diagrams out of that form. And again, you can just relabel the roots in such a way that this leg has P nodes, this leg has Q nodes, and this leg has R node. And possibly this is not the way I drawn it, but let's suppose that P is less or equal than Q, which is less or equal than R. So let's order them like that. Okay? All right? So now, the first observation is that the P has to be has to be equal to 2. The way I'm defining it, that I'm not counting this piece has to be equal to 1. I'm not counting this, the bifurcation node. P has to be equal to 1 because if P is bigger or equal than 2, then E6 extended is inside. If we had that the minimum number of guys is 2, then this diagram has to be inside, and this is not a Dynkin diagram. So that's it. So P has to be 1. So now we only have like Q and R, and Q has to be bigger or equal than 1, and R has to be bigger or equal than Q. If Q is equal to 1, this is allowed, and this is the DR diagram. If we have 1 and the rest is whatever we want, this leads to DR. DR doesn't, yeah. So this is DR minus 3, perhaps. This R here is not the number. For DR, the number of nodes is R. But it's of the type Dn. So let me call it Dn. So if Q is equal to 2, shit, I don't want to remove that. And that's the diagram. Well, I'll remove this. If Q is equal to 2, then, well, so here we are in a situation where P is equal to 1, and the next one has 2. So this is my P that has 1, my Q has 2, and now I wonder what are the possible R's. So if I have 2, then that's E6. Then if R is 2, you have E6. If R is 3, you have E7. If R is 4, you have E8. And if R is bigger or equal than 5, then you have E8 extended, if I'm not wrong. Which is not allowed. Okay? So these are all the possible ones with Q is equal to 2. And if Q is bigger than 2, then you have E7 extended. So this is also not allowed. And that's it. So we've ruled out all cases. So this is very far from full classification because I'm assuming this simply lays thing. And we haven't even ruled out the nasty case, which is loops with some double arrows, which I'm not sure if I'll do this next time or not. Also, Jethro's kind of like sketches this in his notes, but I'll just tackle on non-simply laced cases next class, which I guess is Monday. Any question about today? Okay, so today was very nasty, getting our hands dirty. Next time should be also kind